Welcome to the Foundry by Forge College. I am incredibly excited you're tuning in today. Look, we're going to be popping the hood to examine the actual mechanical engine of blockchain, decentralized execution. If you've ever sat there and wondered how literally thousands of globally distributed total strangers manage to agree on a single, undeniable reality without a boss in the room while you are in the exact right place, let's dive right into this explainer.
So, if you caught our previous lesson, measuring centralization and governance, you know we focused pretty heavily on the who and the how much, the politics of the network, basically. But today, we're shifting gears to the what actually happens. We're moving away from the politics and stepping right into auditing the technical reality. We're looking for verifiable, ironclad proof that the engine is doing exactly what it claims to be doing.
Here is our engineering blueprint for today's explainer. 1. The engine breakdown. 2. Transparency and truth. 3. Determinism in action. 4. Verifying smart contracts. 5. Open source trust. And finally 6. The limits of verification.
Section 1. The engine breakdown. Let's look at the core mechanisms.
Okay, the very first pillar here is replicated state. Think of it like a master blueprint for a massive skyscraper. Now, in a centralized system, only the lead architect holds that blueprint, right? You have to constantly ask them for updates, and you kind of just have to trust they aren't drawing in trapdoors when you aren't looking. But replicated state completely flips that. It means every single full participant in the network holds the exact same up-to-date schematic. Because everyone has a copy of the canonical ledger, nobody, and I mean nobody, can alter the plans without everyone else noticing immediately.
Moving on to the second pillar, deterministic state transition. Now, I know deterministic sounds like a heavy engineering buzzword, but just think of it like baking. Imagine 10,000 independent bakers scattered all over the globe. If every single one of them starts with the exact same ingredients and follows a strictly ruthless recipe, they won't just bake similar cakes, they are going to bake the exact same, mathematically identical cake. Determinism means zero randomness, no creative liberties, absolutely no secret sauce. Given the exact same starting point and the exact same action, you get the exact same result, every single time. And that brings us to the third and final pillar of our engine, the independent executors. These are your diverse miners, validators, or block producers running around the globe. To go back to our analogy, they are the independent bakers themselves. They're the ones actually operating the machinery, taking the inputs, running them through those strictly deterministic rules, and proposing the newly updated blueprint to the rest of the network. When you stitch these three things together, replicated state, deterministic rules, and independent executors, boom, you've got decentralized execution.
Section 2. Transparency and truth. Let's look at the observable outputs.
To actually prove this abstract engine is working, we need an engineer's ledger. For every single theoretical principle, there has to be a real, verifiable signal. Replicated state, that gives us public node RPCs. Deterministic rules, they leave behind reproducible receipts. Execution transparency means the block data is always available to you. And open source principles, they lead to multiple independent client implementations. This core logic, moving away from blind trust and toward cold, hard mathematical proof, is exactly what we emphasize across all the programs at Forge College.
Section 3. Determinism in action. Let's get under the hood.
If we want to guarantee identical outputs, we absolutely have to standardize how we look at data. We do this using hashing algorithms like SHA-256. But here is the catch, and it's a big one. You need stable canonicalization. What does that mean? Well, if node A reads a grocery list from top to bottom, and node B reads that exact same list from bottom to top, the computer gets confused. It sees them as completely different lists, and the network panics. You have to enforce incredibly strict rules, like say alphabetizing everything first, so that meaningless little ordering differences don't break our exact replica.
Which leads us straight into the fundamentals of deterministic replay. Everything must be fixed. Your serialization has to be completely independent of runtime factors. That stable canonicalization we just talked about, it has to ignore things like dictionary insertion order. And honestly, perhaps most importantly, even the failures must be perfectly reproducible. Let's say someone tries to send funds they don't actually have. The balance check must yield a reproducible failure receipt. Every single execution path, whether it's a massive success or a total failure, has to be perfectly reproducible by any verifier sitting anywhere in the world.
So you might be wondering, how do we quickly check if everyone actually matched up? We use something called a state root. This is that deterministic computed fingerprint we just mentioned. Think about it. Sending the entire updated skyscraper blueprint to everyone to double check would be impossibly slow. So instead, nodes just compute this simple hash, this state root. You take your state root, you compare it to the network's state root, and if they match, you know with absolute mathematical certainty that you all produce the exact same new state. It is the ultimate verification stamp.
Section 4. Verifying smart contracts. Let's talk practical scenarios.
Okay, so how do you personally audit a blockchain without trusting anyone? It is a very strict workflow. Step 1. You obtain the block header and the transaction list. Step 2. You extract the specific transaction you care about and its receipt. Step 3. You reconstruct the contract's pre-state, basically, the exact balances right before this transaction happened. And finally, Step 4. You run that deterministic logic locally, right on your own machine. If your math matches the chain's math, the network told the truth. Boom, you just audited a blockchain.
To pull that off, you're relying heavily on receipts and execution traces. Now, I know that sounds like a bunch of heavy jargon, but they're really just breadcrumbs. They are observable, on-chain artifacts that give you a detailed, step-by-step description of exactly how a contract updated its storage. Basically, it's the scratch pad that lets you double-check the block producer's math. As long as you have those breadcrumbs, you can always find your way back to the verifiable truth.
Section 5. Open Source Trust. Bringing in the human element.
Now, beyond the cold, hard math, we have to talk about how social transparency actually amplifies all this technical verifiability. Public code reviews mean you've got hundreds of slightly paranoid eyes actively hunting for flaws. Reproducible builds ensure that the software you're downloading is the exact same as the public code. And independent implementations? They act as an incredible failsafe. If one version of the software has a bug, the other independent versions are going to flag it immediately. It is a massive web of complementary trust signals. Social norms definitely do not replace technical replayability, but they absolutely dramatically amplify our confidence in it.
Section 6. The limits of verification. Let's hit the practical realities.
Because we have to talk about the practical trade-offs here. Reconstructing that pre-state we walked through earlier, well, it can be highly expensive, computationally speaking, if the chain isn't providing efficient proofs. But honestly, the single biggest vulnerability is a reliance on off-chain oracles. If a smart contract relies on an outside price feed, and that outside input is completely opaque or non-deterministic, well, pure on-chain verification gets incredibly complicated. If your state transitions depend on hidden, off-chain inputs, your verifiability completely collapses. And that happens even if the governance of the network looks perfectly decentralized on paper.
Which leaves us with a pretty provocative question to chew on. What happens to trust when execution relies on off-chain inputs that you cannot independently verify? It is a massive critical tension in Web3 design, and it sets us up perfectly for our upcoming lessons on open-source collaboration and oracle mechanics. Understanding this mechanical engine, replicated state, determinism, open-source verification, this is your absolute foundation. To really master these concepts and explore more deep dives into the mechanics of Web3, I highly encourage you to visit forge.college. It's just an incredible educational resource for all of this stuff. Thank you so much for joining me for this explainer, and I will see you in the next one.